welcome to another module in this massive open online course. So, we are looking at the Fourier series representation of periodic signals, that is also we said part of the spectral representation or computing the spectrum of a signal, which is basically representation of the signal in the frequency domain. So, what we are looking at is the Fourier series representation, or also the discrete Fourier series for a periodic signal, correct. The discrete Fourier series for a periodic signal. Let us look at an example to illustrate how the Fourier series can be computed. Let us look at a simple example of a periodic signal. Consider a periodic stream of pulses. For instance, we have each pulse of width d, and let us say this is a periodic signal of period t. So, this is a periodic signal. So, this is minus t, this is minus t plus d. So, this is a periodic pulse signal. The pulse width is d, let us say this d is the width of the pulse, and the period of the signal, the time period of the signal is t. This is the notation that we have used previously also. The time period of the signal is t. This is a particular pulse, alright. Let us set d is equal to t by 4 for the purpose of this example. So, we are setting d equals t by 4, where d equals the pulse width, the width of the pulse in time. Now, let us compute. Now, this is a periodic signal. So, we can compute the Fourier series representation, basically which is nothing but the computation of the various Fourier coefficients of the periodic signal, alright. So, let us compute the Fourier series representation of this periodic signal. So, we want to compute the Fourier series for this periodic signal, and we have shown that the nth Fourier coefficient, correct. We have said any periodic signal x t with period t can be expressed as an infinite sum of complex sinusoids, that is C L e to the power of minus j 2 k 2 pi k f naught t, correct. This C k is the kth Fourier coefficient. This frequency k f naught, remember we said this is the kth harmonic, that is the kth multiple of the, this is the kth harmonic, where f naught equals 1 over t. This is your fundamental frequency. This is the fundamental frequency, and we have also developed the relation to compute this Fourier coefficient C L. This coefficient C L, the nth Fourier coefficient CL for L for any integer L, that is L belongs to the set of integers, that is L equals 0, 1, so on, minus 1, so on. So, L equals, so L can basically take on any L can take on any integer value, and this coefficient CL can be integrated, is given by this integral minus t over 2 to t over 2 1 over t x t e to the power of minus j 2 pi L f naught t dt. This is the relation we have derived for the Lth coefficient of the Fourier series, correct. And what we have said, and in general this integral here need not be only from minus t by 2 to t by 2, it can be over any period, that is this integral need not strictly be from minus t by 2 to t by 2, it can be from any t, that is small t to small t plus capital T, where capital T is the period. So, this integral can be over any period. That is from t to t plus t, that is you can start at any small t and you can carry out the integration from any small t to small t plus capital T, where capital T is the period, because after all the signal x t is periodic. Okay. And now what we are going to do is we are going to derive this for our particular signal. So, we have CL, let us carry out the integral from 0 to capital T. This is integral, as I said, it can be carried out over any period, 0 to capital T of x t e to the power of minus j 2 pi L f naught t. And now this is equal to, remember our signal is a pulse of width capital T by 4, and let us make this height as a, that is the pulse height is a, okay, and therefore this is a for 0 less than equal to t less than equal to t by 4. So, I can replace this as 1 over t, because now it is non-zero only in 0 to t by 4, a times e to the power of minus j 2 pi L f naught t dt, and we are now considering t by 4 since signal is non-zero, only in 0 to t by 4. Only in 0 to t by 4, that is 0 to t by 4 in the period 0 to t, in the period 0 to t. And now a is a constant, so I can bring it outside the integral. So, this is a over t integral 0 to t by 4 e to the power of minus j 2 pi L f naught of t. Now, if L is equal to 0, let us integrate this, let us carry out this integration considering two separate cases. One, if L is equal to 0, that is C0 is a over t integral 0 to t by 4, since L is equal to 0, this will simply be 1 integral 1 times dt. So, this is a over t times t by 4. Once you substitute the limits of integration, so this is a0 a over 4. So, this coefficient C naught corresponding to frequency 0, the Fourier coefficient C naught corresponding to, that is your L equal to 0, that is C L corresponding to L equal to 0, that is C naught, is a over 4. This is also known as the DC coefficient, that is the DC coefficient since it corresponds to the 0 frequency. So, this is basically your DC coefficient. The rest all which correspond to non-zero frequencies, which are basically your k not equal to 0. So, this corresponds to your L equal to 0, this is known as the DC coefficient. All the rest of them which correspond to L not equal to 0, those are known as the AC coefficients. AC is something that is varying with time, and DC is something DC because it is a 0 frequency, it is constant with time. So, this is the DC coefficient which we have evaluated as a over 4. Now, let us evaluate the rest of the coefficients. The general CL for L not equal to 0, for L not equal to 0, we have CL equals 1 over T integral 0 to T by 4 A e to the power of minus j 2 pi L f naught T dt, which is basically bringing A outside, A over T integral e to the power of minus j L f naught T is e to the power of minus j 2 pi L f naught T divided by minus j 2 pi L f naught from the limits 0 to T by 4, and notice that f naught equals 1 by T implies f naught into T equals 1, and we are going to use that principle in the simplification here. So, this is A over T, substituting this, it is e to the power of minus j 2 pi L f naught, let us substitute T by 4, e to the power of minus j 2 pi L f naught T by 4 minus 1 minus j 2 pi L f naught. Now, we know f naught T equals 1. So, therefore, I will use that principle, and also there is a negative sign. So, I am going to simply write e to the power of invert, multiply the numerator also by minus sign or minus 1, and what I get is 1 minus e power minus j pi by 2 L, or 1 minus e by j pi L, 1 minus e power minus j pi L minus pi L by 2 divided by j 2 pi L f naught, and also in the denominator there is a T and then f naught, the product of these two is 1. So, therefore, I can simply write this now also as A, or rather A over j 2 pi L into 1 minus e to the power of minus j pi L by 2, this is your CL. Now, taking e to the power of minus j pi L by 4 common from this, that is, or taking e to the power of minus j what we have, this can be further simplified as A divided by j 2 pi L e to the power of minus j pi L by 4 e to the power of j pi L by 4 e to the power of minus j pi l by 4, and you can see e to the power of j pi l by 4 minus e to the power of minus j pi l by 4 is nothing but 2j sin pi l by 4. That is, if you employ the substitution, e to the power of j theta is cosine theta plus j sin theta, what we have is this is a over j 2 pi l e to the power of minus j pi l by 4 into 2j sin pi l by 4. The 2j's cancel, and therefore, what we have is a over pi l sin pi l by 4 times e to the power of minus j pi l by 4, and this is our coefficient e to the power of, and this is our coefficient, correct. So, this is your lth Fourier series coefficient where L not equal to 0. So, now we can finally write CL equals A by 4 for L equal to 0, CL equals A by pi L sin pi L by 4 e to the power of minus j pi L by 4 L not equal to 0. And further, if you are interested only in the magnitude, so therefore, we have derived the lth Fourier series coefficient for this periodic pulse signal, and further we can look at the magnitude, that is magnitude of this signal, magnitude of CL is magnitude pi L sin pi L by 4 e to the power of minus j pi L by 4, and magnitude e to the power of minus j pi L by 4 is 1. So, this is simply magnitude A over pi L times sin pi L by 4. This is known as the magnitude spectrum. Okay. This is known, in general, the spectrum is a complex quantity. There is a spectral coefficient as the lth frequency component, that is at L times f naught, is a complex quantity. So, it has a magnitude and a phase. The phase constitutes the phase spectrum, the magnitude of CL constitutes the magnitude, corresponds to the magnitude spectrum. Alright. And also, as I have said, in this simplification we have employed the fact that magnitude e power minus j theta equals 1, that is magnitude e power minus j pi L by 4 is equal to 1. So, this shows basically the computation of a, so this is magnitude CL. So, this is basically a simple example for the computation of a, so this is basically a simple example for computation of the discrete Fourier series, that is the discrete Fourier series spectrum of this periodic pulse signal with period capital T and pulse width capital T over 4. Alright. Now, let us look at another important aspect of a periodic signal, that is, let us look at the power of the periodic signal in terms of the Fourier series. We have already looked at the power. Let us revisit this again, that is, let us look at the power of the periodic signal. So, let us revisit this power computation again. Let us look at the the power of a periodic signal, correct. We have already seen that for a periodic signal, that is for a periodic signal x t, the power is defined as P, or the power is defined as, well, P equals 1 over T integral 0 to T. Again, in fact, this integral can be carried out over any period. So, 1 over T integral 0 to T magnitude x t square dt. This is the power of a periodic signal. This is the power, the expression for the power of the periodic signal x t, that is 1 over T 0 to capital T magnitude x t square dt, where again of course, it goes without saying capital T is the period, which is this very specific quantity, which is the period, fundamental period of this periodic signal x t. So, this is the period of x t. Now, let us represent x t in terms of its Fourier series representation. We said any periodic signal x t can be represented in its Fourier series. So, x t equals summation k equal to minus infinity to infinity c k e to the power of j 2 pi k f naught t x conjugate. Now, to compute magnitude x t square, we need x conjugate of t. So, x conjugate of t can be given as the following. Let us employ a different index. It is simply the index. So, I can change it. So, it is minus infinity to m equal to minus infinity to infinity c m e to the power of, that is conjugate of this j 2 pi m f naught t, which is the integral m equal to minus infinity to infinity c m conjugate e to the power of minus j 2 pi f naught t. This is your x conjugate of t, correct. Now, let us compute the power of this periodic signal. The power equals 1 over t integral magnitude x t square, which is x t into x conjugate t dt, which is 1 over t integral 0 to capital T x t. We have already developed the expression. X t is summation k equals minus infinity to infinity e to the power of j 2 pi k f naught t times x conjugate t, that is m equal to minus infinity to infinity c m conjugate e to the power of minus j 2 pi m f naught t whole into dt. Now, let us expand this product, remove the brackets and bring multiply these things term by term, the product, that is the sums in both the summations term by term, and what we are going to get is basically 1 over t summation 0 to t k equal to minus infinity m equal to minus infinity to infinity c k c m conjugate e to the power of j 2 pi k minus m f naught dt. Now, what we are going to do, similar to our derivation of the Fourier series coefficient, what we are going to do is we are going to interchange the summation and the integration operations, all right. And what we are going to have then is basically interchanging summation and, or rather interchanging the summation and integration operations. Interchanging the summation and integration operations, what we are going to have is the power. I am going to bring the summations outside, summation k equals minus infinity to infinity, summation m equals minus infinity to infinity, and Ck into Cm conjugate into 1 over t times integral 0 to t. If you can look at this 1 over t integral 0 to t e to the power of j 2 pi k minus m f naught t, that is e to the power of j 2 pi k minus m f naught t dt. And if you look at this, we have already seen this, that is for any k not equal to m, that is 1 over t integral 0 to t e to the power of j 2 pi k minus m f naught t dt, that is if k not equal to m, this integral is 0. If k equal to m, this integral is 1. Remember, we said this integral is therefore delta k minus m. This integral we have already derived this. This is simply your delta k minus 1, that is equal to 1 if and only if k equal to m, 0 otherwise. So, this is 1 if k equal to m, this is 0 otherwise. So, this is summation k equals minus infinity to infinity, summation m equal to minus infinity to infinity Ck Cm conjugate into delta k minus m, and therefore, in this double summation the only term only terms that survive are when, because delta k minus m equal to 0, if k is not equal to m, the only terms that survive are the terms corresponding to k equal to m, and therefore, when k equal to m, Ck into Cm conjugate will be Ck into Ck conjugate, which is magnitude Ck square, and therefore, in that scenario this will be k equals minus infinity to infinity Ck conjugate equals summation k equals minus infinity to infinity magnitude Ck square, and this is the expression for the power. And what you can see is you have a very nice expression for the power of the periodic signal in terms of now the Fourier series coefficients, that is the power of the periodic signal is nothing but the magnitude, there is nothing but the sum square of the magnitude of all the Fourier series coefficients from minus infinity to infinity. And this is a very interesting and this is a very elegant expression for the power. So, therefore, what we have is the power has two expressions. One is we have the traditional time domain expression 1 over t 0 to t magnitude xt square dt equals summation k equals minus t minus infinity to infinity magnitude t Ck square. So, now we have a frequency domain expression also expression for the power in the frequency domain, that is in terms of its spectrum, and this is known as the Parsevals relation. This is a very popular result. This is known as the Parsevals theorem, that is which gives us the power of the signal, and what this is really giving is the power of the signal in terms of the spectrum. This is giving the power in terms of the spectrum. Alright, so we have 1 over t integral 0 to t magnitude x t square dt, which is the power, it is a time domain computation, and now we also have a very interesting expression to compute the power from the spectrum, that is in the frequency domain, that is magnitude k equal summation k equal to minus infinity to infinity magnitude ck square, where ck is the kth Fourier series coefficient. Alright, and this is a lot of applications, and it is also a very interesting result. This is known as the Parsevals theorem. It gives an equivalent way to compute the power from the, and it shows that this two things, that is power computed from the time domain and also from the using the coefficient, the spectral coefficient in the frequency domain are equal, and helps us to characterize the power distribution amongst the various spectral components. For instance, one can think of Ck or magnitude Ck square as the power in the kth spectral component, that is power at the harmonic k times f naught, and that gives us a very interesting interpretation. Of course, we are going to keep looking at such this interpretation, alright. So, remember this, and we are going to keep looking at, once we look at the Fourier transform of a continuous signal, again we are going to relook at this interpretation of what is the distribution of the power amongst the various spectral components, that is amongst the various frequency components, and this Parsevals relation gives us a way to interpret this power of the periodic signal as being distributed amongst the various spectral components, which magnitude Ck square characterizing the power of the signal in the kth spectral component or at the kth harmonic k times f naught. Alright. So, let us conclude this module here. What we have looked at in this module is an example of how to derive the discrete Fourier series representation of a simple periodic signal, that is a periodic pulse train, and also the Parsevals theorem for the power of a periodic signal. Alright. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.